All right, let's get started. So today we're going to continue our discussion of network security. And just to remind you guys where we left off last lecture, we were looking a lot at the security of the underlying network protocols like TCP, IP, and UDP. And basically the summary is that you should really think of the adversary there of being able to observe and modify all the data in a TCP IP connection. So TCP IP on its own isn't really going to provide us very strong, if any, security guarantees. So inevitably what you have to do in order to build secure network systems is to rely on cryptographic techniques to some degree, to sign, encrypt, authenticate messages. And we're going to have actually quite a large number of lectures in this class, probably on the order of 5 or so, that are all about how do you use cryptography to protect certain kinds of network communications. And the reason it's important to look at these examples is that directly using cryptography is quite tricky, subtle, and error-prone. And as you saw in this paper, even a fairly straightforward enough plan to just encrypt one TCP connection is actually quite tricky to get right. These people were smart, but they made mistakes, and the subsequent protocols to the one you read about also had mistakes, and the one after it had mistakes, and now we think, we're pretty good 25 years later. So it's important to really figure out good abstractions for what kinds of things we should build with cryptography once and for all, and then build applications on top of these abstractions. And the abstraction that we're going to look at in this lecture is probably one of the simpler things. It's this notion of a secure channel. And in later lectures, we'll look at other kinds of things you might want to do over the network with cryptography. And each one of them ends up being tricky. But let's try to understand the simplest abstraction you might care about, sort of providing a secure channel between two parties. And what a secure channel is trying to do, what SSL in this paper is trying to do, is really connect a client and a server together over a network. And because they're connected to each other over TCP IP, you can't really assume anything about the underlying bytes being sent, but SSL is going to provide sort of this tunnel, if you will, that protects the communication between the client and the server, such that if the adversary somehow, observes or modifies the packets being sent through this tunnel, hopefully some security guarantees are going to be preserved. We'll see which ones are preserved, etc. But this is a very nice abstraction in many ways because we can spend a significant amount of time figuring out how to build a secure channel. Like this paper and many subsequent pieces of work worry about how to build this tunnel abstraction. And once we have it, we can layer lots of things on top of this secure channel. So for example, the stuff running inside of this channel might be HTTP. So HTTPS is typically used to refer to HTTP inside of this TLS protected secure channel. Could be SMTP for sending email. Could be IMAP inside of this channel for retrieving email, etc. Lots of protocols these days rely on this secure channel abstraction. So this is a pretty common way to use crypto in practice, is that we figure out what are good sort of building blocks to use, and then hopefully we can build applications in terms of those building blocks or primitives, rather than quite using crypto directly. Directly using crypto ends up being tricky, as we'll sort of see in a bit. So that's sort of the plan for today. We're going to look at this protocol that the paper talked about. I guess the paper's specific protocol was SSL. This was the old name for what's now called TLS. They're basically the same protocol. SSL was the name when Netscape Corporation was in charge of this, when they developed the web in some sense. And then this transition to being managed by some broader organization, IETF, and it changed the name to TLS. But it's basically later versions of the same protocol. And the browsers today use a much more recent version of TLS, 1.3, than the version of SSL that you read about in the paper. But the protocol, in some sense, is really an incremental evolution over SSL 3 to get to where we are today. So it's still literally SSL 3 isn't used anymore. It has some flaws that people have discovered over time. But effectively, it looks quite a bit like SSL 3 still, with some fixes. All right, so that's sort of the context, what we're going to look at. Make sense? Hopefully. Questions so far? All right. So to try to understand how we're going to build this secure channel abstraction using crypto, it's worth revisiting what are the crypto primitives we're going to be building on. We've talked about these a couple of times already, but the details are going to matter for this discussion of how to build a secure channel, so let's revisit them again. So we're going to be using two families or two kinds of cryptographic primitives. There are things that are relatively efficient that are using what's called symmetric key cryptography, and then we'll have public key cryptography that provides some fancier operations, but with more performance overhead. That's one way to think of it. So let me tell you about the symmetric key encryption primitive. So you can generate a key. So I'll sort of spell them out in this sort of abstract spec view. So you can call keygen and get a key back. And the kinds of things you can do with a key is you can encrypt and decrypt. So you can encrypt using a key, and if you got a message, you'll get what's called a ciphertext back. And then you can decrypt it. If you have the right corresponding key, or the same exact key, you can get your message back. So that's the way you encrypt with a symmetric key. And the reason it's called symmetric key crypto is because the same key is used for encrypting a message and decrypting it. And in addition to encrypting and decrypting messages, you might want to authenticate a message, meaning that you might want to prove that no one modified this message. Encryption doesn't really provide that. If you have some encryption and someone modified the encryption, it'll still decrypt. It might decrypt to something surprising or garbage or who knows what, but you have no idea if someone modified it. So for authenticating messages, there's an operation called a MAC, or a message authentication code. You give it a key and a message, and it'll give you a tag T. And the way you use this MAC is that you can, if I and my friend share the same secret key, I can compute a tag of a message with my key, and I can send it to my buddy. But no one else can compute the tag of this message if they don't have a key. And in particular, they can compute tags of other messages if they don't have keys. So my buddy can check that the MAC that I sent him, this value matches what they recompute on the message they care about with the same key. We'll look more in details of how we actually apply this in the context of some protocol in a bit, but this is sort of the API or function level spec for this. And the kinds of schemes that are used here are things like you might hear about AES, DES is like a really old version of this that probably shouldn't be used anymore, and so on. These are the kinds of primitives that underlie this symmetric key cryptographic constructions. Make sense, hopefully? Any questions about this? So one downside of this is, of course, you already have to share a key with someone to encrypt or decrypt or authenticate messages. So there's a whole other family of cryptographic operations called public key cryptography. And here, the big difference, in some sense, is that keygen is going to give us a pair of related keys called a public key and a secret key. And there's two kinds of things we might do with them, similar to encryption and authentication. We can also encrypt. So you can encrypt with a public key a message, and you get a ciphertext out. And you can decrypt. To decrypt, you need the secret key. And if you have the secret key and a ciphertext, you can get the message out. But if you don't know the secret key, you can't get the message out. And very much like we had this duality between encryption and authentication, similarly in the public key world, just because a message is encrypted doesn't mean that it's a valid message that someone correctly sent to you or any specific person sent to you. So we need to be able to authenticate messages. And here, this takes the form of a signing and verification pair of operations. These guys we looked at already in a previous lecture to some degree. So if I have a secret key, I can sign a message M to produce what's called a signature. And there's a corresponding operation called verify that anyone with the corresponding public key can use to check if a signature is a valid one for a message. And the security spec here is that if the person with a secret key produced the signature, then, yeah, this verify will pass. But someone without the secret key cannot guess or synthesize a signature for a message that's going to look legit. So that's roughly the spec. We'll look in detail again how these get used. And just to give you some terminology for what these schemes usually are, these are schemes like RSA or various elliptic curve constructions or Diffie-Hellman-based constructions, etc. These are the kinds of schemes that you might find under the covers of an implementation of these public key operations. Make sense? Any questions? Guess we'll see them used in a second, but hopefully straightforward enough. All right, so let's try to design one of these secure channel protocols, and the goal here is going to be to try to appreciate some of the subtleties that go into using crypto to achieve a secure channel implementation, and maybe cook up a couple of useful techniques, sort of both build up intuition for the kinds of things that go wrong, and build up some intuition for how you go about solving these problems and building a more robust protocol, and we'll arrive at something that looks close to what SSL3 ended up being. So here's a somewhat naive protocol that we'll start with for a secure channel. And very much like SSL, we're going to structure this protocol in two phases. So most cryptographic protocols often use both public key and symmetric key versions. The public key operations are typically used to establish a shared key in the first place. So when I want to connect to someone or talk to someone or interact with any other computer over the network, I would first use some public key operations to set things up so that my computer and the other computer agree on some secret bits of information. And that secret bit of information is going to end up being a key for symmetric key operations. And the reason for that is, to some degree, because symmetric key operations are way faster. So these kinds of things operate at gigabytes per second. These operate at sort of 1,000 operations or 10,000 operations per second. So they're quite a bit slower. But they offer some cool functionality. So we're going to structure our protocol into these two phases. One, very much like SSL, is going to be called a handshake. This thing is going to initiate connections and give us a shared key. And once we have a shared key, then we can actually go ahead and start sending application data between our two computers. So let's look at what this protocol might look like. So we're going to have a client over here and a server on the other side that want to communicate securely, like this secure channel pipe. And what this protocol might look like is the client sends a message to the server saying, okay, I want to connect to you. This might be start a TCP connection, SYN, ACK, the kind of stuff we looked at on Tuesday. And in response, the server is going to send back a public key of the server. So probably the server has a public key of the server and a secret key of the server generated ahead of time. The server sends me back a public key. Now, what the client could do is generate a symmetric key, a fresh key for this session. It's going to be called a session key, K, and the client is going to send it over to the server, encrypted with the public key of the server. And now, the server can get this message and can decrypt it. In fact, only the server should be able to decrypt it, because only the server has the corresponding secret key, SK sub S. And at this point, the server can decrypt the message and get the key K. Now both the client and the server have this key, and now they can start sending each other messages that can just be symmetrically encrypted with this symmetric key K. So, does this protocol make sense? It's got a couple of problems. We'll look at them in a second, but any questions about how this protocol sort of works as it is, or why this works? Make sense? All right. Also, feel free to ask questions through Kevin anonymously if you want as well, as usual. All right. So what are some of the problems with this protocol? Any guesses? Yeah? Sorry, so you're saying everything is plain text up until you start encrypting here. So that's true. Okay, so what kind of an attack are you thinking could take place? Yeah. So you're worried about the public key, yeah? Uh-huh. Okay, so how would an adversary, so you're saying, okay, there's potentially an attack where an adversary is going to sit in the middle and do something to get this key. So how would this adversary work? You're thinking. The private key from, yeah. I see, so you're thinking that the adversary would send a fake public key to the client. Yeah, indeed. Okay, so one thing that's worth observing is actually, I believe this protocol is secure if you have passive attackers. So if the adversary just monitors the network, this protocol is actually not too bad. It has some nice properties, meaning that an adversary that just monitors the packets can't really get the data. They can get this public key, but that doesn't tell you anything. They can get this encryption, doesn't tell them what the key is, and they can get this stuff, but it's also encrypted. But, as you rightly point out, if an attacker can all of a sudden intercept some messages on the network, then we have a problem. And the way to sort of think of this problem is that we need to authenticate who the server is. So let's try to sketch out what this attack might look like. So as a client, what's the client going to do? We already know. Here's a protocol. I connect, and then I expect some kind of a public key back. And I don't know where this public key came from. It just like some bits appeared on the wire. And then when these bits appear on the wire and I receive them, I'm going to send my key out on the network, encrypted with that public key. And then we'll sort of start using this key. So one way to understand these network protocols is that you really have to look at each node in isolation, because even though I drew this diagram of the client and the server, really the client has this very local view. Like, I don't know, I sent some bits out, something came back. Then I sent more bits out on the wire. I don't know why I'm doing this, but that's the plan. And in this view, you should now probably be thinking the attack that Asel pointed out, which is that if my bits actually go to someone that's not the server, it's maybe some adversary in the middle, the adversary can respond with the public key of the adversary instead of the public key of the real server. So the adversary is going to have their own public key and secret key, and the adversary can just have the client effectively establish a connection to the adversary, and now the secret key that the client generated is known to the adversary over here. Moreover, the adversary can go sort of in the back and actually connect to the server behind the scenes. The adversary can speak the same exact protocol to the server down to actually giving the client's key to the server. So as far as the client and the server can tell, nothing funny is going on because they end up with the same key. And in fact, they can continue communicating with the adversary being able to observe and potentially modify any of the messages that they're sending between the client and the server. Does this attack make sense? So if an adversary can modify the packets, the adversary can sort of speak one side of the protocol to the client, get the key, speak the other half of the protocol to the server, also with the same key, different key, doesn't really matter, and then the client and the server think they're talking to each other, but the adversary both modifies and observes all the traffic. So it seems kind of damaging. Does this make sense? Of course, it's only possible if you have an active network attacker that can tamper with your packets. So how do we go about solving this? Well, there's sort of two solutions to this plan. One is to rely on some authority that's going to be in charge of assigning public keys. This is typically called certificates. And what this authority design looks like is that we're going to have some kind of a server called an authority server, or a certificate authority, CA. And the certificate authority is going to maintain a giant table of everyone's public keys. It's going to have a table that says something like, here's the name of the server that you want to connect to, and here's the public key. If that server is Amazon.com, then here's the PK of Amazon. If the server is MIT.edu, here's the public key of MIT, and so on. And this certificate authority is going to help our client and server establish a connection to each other. And basically the rule is the client is going to ask the authority to confirm what is the key the client should be expecting. Now, of course, the client has to figure out who they want to connect to, because so far in the picture, the client actually, in some sense, didn't really know who they're trying to connect to, some server S. So in order for us to be able to provide a meaningful security guarantee, we're going to tie this to the intention of the client by tying it to the name. So the client wants to connect to something called Amazon.com. Well, they're going to talk to whoever's public key is registered under Amazon.com in this authority servers table. So the plan is the client is first going to effectively talk to the certificate authority and get something like maybe the client queries the authority for MIT.edu, get back PK MIT, and then the client can run that protocol we had up there in order to establish a connection to MIT.edu. Well, there's a couple of things that are important here. One is the client really needs to know how to securely talk to the certificate authority. So the certificate authority needs a public key of its own, a PKCA and a secret key of the certificate authority, so that a client can establish a connection or trust relation with the certificate authority. And we could actually have it so that the client really uses that protocol to talk to the CA, open a connection, ask the CA for a table entry, and then use that same protocol to connect to MIT.edu. Now, in practice, what people do is they don't want to have the certificate authority be on the critical path of every connection being opened on the internet. So instead, they do something else, which is they pre-sign, the certificate authority pre-signs messages that basically provides a single entry from this table in an authenticated way. So what we're going to have is the client is going to actually talk to the server with the protocol we had before. You first connect to the server, but then when the server sends its public key back to the client, it also is going to attach a statement from the certificate authority saying, yep, that is the correct server's public key. And what this certificate is going to look like is that the certificate is just a signed statement by the certificate authority where the message basically says, MIT.edu is PK MIT with the key filled in. So that's the kind of signed message that the certificate authority is going to generate for the server here, if that was the MIT server. So certificate authority gives the signed message to the server S, and now the server S can present the signed message whenever a client connects. And the reason the client should now believe it's talking to the correct server is because hopefully the certificate authority will only sign messages that are actually legit from this table, and somehow the certificate authority knows everyone's public key. We'll talk about that next lecture, next week. But then the client can know that there's no attack going on of this flavor, because if an adversary tries to supply a public key of their own, they're not going to be able to attach a certificate that has the right name in it. That make sense? Question? Oh, absolutely. Yeah, okay. So you're asking, okay, what if an adversary gets the certificate from MIT's server? Like the MIT server is sending it to anyone that asks for the matter, right? So what happens if an adversary gets the certificate? Well, the adversary can use the certificate in its own response to a client. But what public key does the adversary give the client? If the adversary gives their own public key, like in this attack we saw here, it's not going to match the public key in the certificate. So the client is going to say, well, the server gave me this public key, and it gave me a certificate that says MIT's public key is this other thing. Well, that's no good. It's not MIT, the server I'm talking to. Alternatively, this adversarial server will give MIT's public key and the correct certificate, and that's all great and good. This is how MIT's server would normally work. But now, this secret key that we're going to encrypt in this step is going to be encrypted with the real public key of MIT's server. And now the adversary cannot decrypt it like in this attack. So the certificate, you're right that you can replay it, but the really cool thing about certificates is they're completely public information. An adversary can be assumed to have all the certificates it wants. It doesn't actually help them. There's another question back there. An excellent question. How does the client get the public key of the certificate authority? So the client needs PKCA. This is absolutely crucial. And that's an interesting question to wonder. Like, you guys go out and buy a laptop, you start browsing the web. Where's PKCA coming from? And the answer is basically it gets pre-installed, pre-distributed. So when you install Windows or Mac OS, either Microsoft or Apple, behind the scenes have somehow talked to all the CAs that matter in the world, or whatever, some set of CAs, leave it at that, and they package those public keys of certificate authorities with your computer. And when you download Chrome or Firefox, that binary comes with public keys of certificate authorities that that browser will trust, for example. So we'll talk much more next week when we talk about certificates specifically, but that's roughly how it is. You have to bootstrap this from someplace to define sort of which universe do you want to live in. Yeah. You had a question? So you absolutely have to get this PKCA from somewhere. And if you buy a laptop from some hardware manufacturer that installs a bad PKCA here, like your whole universe is bogus. You're talking to a bad certificate authority that is making up public keys for anyone that knows. Well, yeah, so like, well, if you don't bootstrap right, you might never be in the right internet in some sense. Now, in practice, probably you'll notice, but it's hard to give security guarantees if you don't want to trust where your sort of device and software initially comes from. It's a pretty hard problem to solve in some ways. Absolutely. Question back there? Okay, so you're wondering, okay, like, well, what do I do as a person, like, with these public keys of certificate authorities? So most browsers actually will let you look at all the certificate authorities that your browser trusts. There's a couple hundred of them in your browser. I would worry more about, like, some poorly managed one more than one that's run by the government, because the government will just compromise the poorly run one instead. They don't need to run their own. But indeed, that's a real concern, and you could try to manage your own list of certificate authorities. The problem is that suppose you don't trust some certificate authority. Well, you go to a website and they use the certificate authority. Now your website is going to break until you start trusting that. It's not like you can ask the website, hey, I only trust this certificate authority. Please go get a certificate from them. The protocol isn't set up this way, and as a result, you don't really get a choice of what certificate gets presented to you. Now, that might or might not be okay for your use case, but yeah. Such as the protocol. Other questions? Yeah. So one question is, suppose that, this is an okay key now, but 5 years down the line, someone steals your secret key. So what's the answer? Well, the answer is mostly that there's three answers. One is there's expiration dates in these certificates. So hopefully you set a certificate to be valid for 1 year, and then next year you should get a new certificate, and maybe you'll get it for a new key at that point. The second answer is that some certificate authorities try to have some kind of a revocation protocol for revoking certificates. It rarely works well, for reasons we'll talk about next week, but, The third answer is people don't really have a great plan for these kinds of key compromise. So neither of these two answers are super satisfactory in some sense. And people don't really know how to do much better. Yeah. Other questions? Yeah. Maybe, yeah. So we'll talk about some kinds of replay attacks in a bit, and some things we could solve. Some things are hard to really address, but yeah, some things work. All right, so I wanted to mention another alternative solution, which is called trust on first use, or TOFU as an acronym. And it's sort of a non-solution, but it works extremely well in practice. And for example, SSH uses TOFU, whereas your browser does something more like this. So in trust on first use, the idea is that you really do speak the protocol that we drew out over here under naive protocol. Well, SSH does something slightly more fancy in some ways, but in terms of public key negotiation, SSH just takes this key that the server gives you if this is the first time you've talked to that server. And your SSH client is just going to maintain a table of servers you've connected to in the past. So if I SSH into, athena.dialup.mit.edu, then the first time my client connects, it has no idea what the public key should be, so it's just going to assume it's okay. and it's going to write it into a local file in my home directory. And then later, when I connect again, it's going to make sure it's the same key. So the threat model sort of is that the first time you connect to a server, hopefully you got the right server. There was no active attacker. Even if there was a passive attack, that's not a big deal for us here. And then, once we've saved the key here in the file, then we're secure from that point on. Well, it is what it is. It's more decentralized, doesn't require some central certificate authority to exist, but it doesn't work so well against active attacks that try to attack you the first time you connect to a server. But if that's not the attack that you're worried about, this works out well. This make sense? Sort of the best you can get without involving some grand certificate authority in the middle. Questions? All right. So that's one problem, how to authenticate the server. The other problem we want to look at in that naive protocol is how do we actually authenticate the messages? So what's the problem that I want to describe here? So here's a potential problem, which is that we're going to run this protocol. We're going to do the handshake with certificates maybe. Everything is going to be good. We're going to establish a shared key, K, between the client and the server. And what we're going to do is send an encryption now under this key of, I don't know, send $1 to Bob. Maybe this is a bank. And now the question is, okay, well, what can the adversary do? Well, the adversary can't really decrypt our message. It's encrypted with a secret key, and they can't get this key from anywhere because they don't have the right certificate, etc. But this message that's being sent on the wire is just a sequence of bytes. I mean, I don't know exactly what these bytes are, but there's going to be some byte representing the encrypted one. Most encryption schemes work sort of block or byte at a time. So I don't know, maybe there's like some big X that's the byte representing the encrypted one. And an adversary can just corrupt this byte. I don't know, flip a bit, and now it's Y in the same sort of encrypted blob. The adversary doesn't know what was being sent, but maybe in this case, the adversary knows you're transferring money. The adversary knows this is a bank. And the adversary just corrupts the position where you specify the money being sent. The thing to keep in mind, though, as I was mentioning before, is that encryption doesn't give us any authentication. One way to appreciate this fact that encryption is absolutely not providing any authentication, one sort of intuitive way to realize this is to think of the API of decrypt. So when you decrypt using a key, some ciphertext, you always get a message back. It doesn't matter if the message was corrupted. Decrypt always succeeds. So if an adversary corrupts your message, decrypt is still going to decrypt. It's going to give something back. And if the application is going to treat this as a bank transfer, some bank transfer is going to happen. The only question is with what amount. So in this case, for example, if you flip a bit in this, maybe the decrypted message is going to come out as, I don't know, maybe this was the high bit, so it's 129, maybe like 128 plus 1 to Bob. So this seems damaging if the adversary is able to corrupt messages and have the server act on these corrupt messages. So we need to provide some authentication of the messages themselves being sent. Does this problem make sense to you guys? I mean, the specific way in which corruption of the encrypted message is going to affect the decrypted message depends on the exact scheme. But as I mentioned, pretty much all of them work on some kind of a per byte or per block level, and you'll be able to corrupt or have some maybe localized effect. Depends on the encryption scheme. So the solution to this kind of ciphertext modification problem is to actually use a message authentication code, or this MAC construction, to authenticate messages. So the way that the sort of fixed protocol is going to work is that we're going to have the client, and again, after all the handshake steps have happened, we're going to send both the encryption of the data and an authentication of the thing that we just sent to make sure that an adversary can't send something else. So in particular, we're going to compute a ciphertext C, which is, of course, the encryption under some key of the message. And we're going to send an authentication tag T, which is this MAC function we talked about way back there, of the ciphertext that's being sent. So one detail that turns out to be important is that we shouldn't really be using the same key for two different operations in a cryptographic protocol. So really, these should be K1 and K2. One key should be used for encryption, another for authentication. Otherwise, you might have some unfortunate interactions between the two schemes, and it might weaken one or the other. So what this means is that actually during handshake, we're going to agree on two keys, K1 and K2. K1 is going to be used for encrypting messages. K2 is going to be used for authenticating them. So now, on the server side, we've also agreed on K1 and K2 during the handshake. And now, when the server gets a message, it's first going to check, is T, the tag inside the message, actually equal to the MAC of the ciphertext I just received? So is the tag consistent with the ciphertext? And if they're consistent, then the security property of the MAC tells us that only the other person that has K2 could have possibly computed this tag on the ciphertext C. And as a result, it's safe for us to now decrypt the ciphertext C and then process the message. So this way of authenticating messages sent over the network is going to defeat these ciphertext modification attacks. Does this make sense? Any questions about this? Yeah. So your question is, okay, does a website have to worry about like the order of stuff in this message, for example? So in this attack, right, it seems like it's kind of annoying that you worry about this stuff now. If you have a correct, secure channel, you don't have to worry about this stuff. So this is what I mean by it's tricky to use cryptography correctly. If you just directly go for the cryptographic primitives, you now all of a sudden worry that like a whole block could be corrupted. That's a mess. So the whole goal of this discussion is how to use cryptography in a way that gives you the cleanest possible secure channel abstraction. So the application needs to worry about the fewest weird things possible. So, and in particular, if you do this kind of authentication, compute the MAC on the ciphertext, then that actually gives you a pretty clean abstraction. There's a few exceptions we'll talk about later, but by and large, you can just treat this as you don't have to worry about the order of things in your message. Just send the whole message will come out clean on the other end. One difference you might notice actually between how this construction looks and what the paper talks about is that in the paper, in SSL2 and SSL3, the designers actually had it slightly differently, which is that they first computed the MAC on the plain text message, and then they encrypted everything. They encrypted both the message and the MAC together. And this turns out to have actually given a rise to like a subtle attack that was like the reason people stopped using SSL3. And reordering the MAC and the encryption in this way turns out to be just like the right way to do it. So this is turns out to be a much better construction, much more robust against various attacks. If we have time at the end, we'll maybe discuss exactly what this attack looked like. But like here's a super subtle detail. You would have thought, could have just authenticated the message first and then encrypted the whole thing. But no, it's like these kinds of really subtle ordering details matter. And as a result, like TLS 1.3, which is the latest thing, doesn't look too much different from SSL3. It's just like, reorders a couple of things that really matter. And but details do matter. All right, so that's the plan for how to deal with message authentication, which is that we have to explicitly include authentication code for the message itself. Make sense? Questions about that stuff? All right, so now let's talk about another interesting problem, which is that an adversary might send duplicate messages. So we've already started thinking a little bit about duplicate messages when we were discussing certificates, when we were thinking, the bad guy could get a copy of our certificate and try to use it. And in the certificate case, it turns out to have not been a big deal. We somehow managed that because the certificate is okay to duplicate. But in our protocol so far, duplicating the application data could be problematic. So here's a potential problem for us to worry about, which is duplicate messages So here's an attack. Suppose that, again, we have the same, I don't know, maybe a bank application where the client sends this authenticated message to the server. And the message is an encryption with the encryption key K1, I don't know, send $1 to Bob. And it also includes the MAC, so to authenticate the message of the ciphertext. All good stuff. There's no way an adversary would have been able to send this message before we send it ourselves. Adversary wouldn't have been able to fake this message. But once the client sends this message, now the adversary has this message. So now the adversary can grab a copy of this message by monitoring it on the wire and send it again to the server. And by the rules we've talked about so far, the server is going to check the MAC. MAC looks good. It's going to decrypt the message. The message says, send $1 to Bob. Server's going to do that again. So cryptography is a stateless primitive. It has no memory of what happened before or after. It's like purely mathematical functions we're computing. So we need to do something else in order to deal with this duplicate message problem. This is often called a replay attack in cryptographic literature. So does the problem or attack make sense? Any questions about what goes wrong here? All right, how do we fix this? Any thoughts? Yeah? So we can include the time in the message. Okay, so we can try that. So that's probably a good start. So let's see. So for a replay attack, so one possibility is, I guess, our encrypted message could be an encrypted message of the message and also, the current time. Okay, so we send this message to the server. What does the server do with this message now? I guess the rule must be that, if the time is like maybe within the last minute, we should process it. But time alone doesn't quite help us here, right? Because an adversary could immediately retransmit this message, like within the same second. So the time in the message here is going to look fresh. And it's also going to look fresh in the retransmitted message. So you're right, if the adversary keeps this message around for a day, maybe the server can say, oh, this is like too old. But it might still look fresh. Yeah? Sequence number. Yeah, okay, so that's a good idea. This is actually what what SSL3 does. I think the paper mentioned this in passing, which is that in SSL3, every message actually comes with some kind of a counter number. And there's basically a counter that sits at the client that starts with 0 for every session. So when you open a connection, you're going to keep track of all the messages you've sent. You're going to start with 0, and you're going to increment for every message you send. And on the server side, you also have a counter. And the server is going to be expecting all the messages to be in order. So when the server receives a message from the client, it expects the counter number to match the server's counter number. So the first message it gets must be counter 0. And then it's going to increment its counter number so that if message 0 is sent again, the server is going to drop it because it's a duplicate message. So fundamentally, in some way or another, I think what this counter scheme is getting at is that we have to keep track of the messages we've already seen. We need some state for this. So a counter works pretty well for stream-based connections. So the secure channel abstraction is a pretty good fit for counters. TLS uses a counter scheme effectively for all of its messages. Counters might not work so well if you don't have an ordered protocol. So if you're designing something that might run over UDP, then a counter might not be a great idea. And in that case, you still have to keep track of all the messages you've seen, but you can't do it as succinctly as a counter does. So in a non-stream or a non-counter based protocol, you might actually have the server having to keep track of all the messages it's seen in this session or something like this, or maybe combine it with time, like include a time and include the time in the message, and the server keeps track of all the messages from the last 5 minutes, and anything before 5 minutes it can forget because it will then reject messages that are older than 5 minutes. So some combination of schemes like this is important to make sure that participants drop duplicate messages. Question? So okay, your question is like, doesn't AES carry any state? So in fact, AES does not carry state. AES is just like a purely mathematical thing. It, like, given an input, it'll give you the same output every single time. There's certain modes in which you use AES that might use a count or some other initial seed. And if you change that seed, then you might get some different properties from AES. But then, in fact, it is basically just using counter, but then somehow tying it into the encryption function at a deeper level. You still need the state. And in fact, the way in which the most recent version of TLS uses AES, it's called this GCM, Galois counter mode of operation. It's a scheme where basically AES, or AES GCM, expects the TLS stack to give it a number for every single block of data you encrypt, and then it's going to encrypt and authenticate each block at a time. So the encryption is fundamentally going to rely on your application or secure channel implementation keeping track of this counter for you. Absolutely, yeah. So you can think of that as more of an optimization that sort of combines AES with this counter thing at the same time. Yeah. Other questions back there? Okay, so your question is, okay, well, yeah, the adversary knows you start at 0. Can this somehow be used against the protocol implementation? And I guess the answer is we figured out, as a sort of the security community, as cryptographers have figured out how to build encryption schemes for which it's okay for the adversary to know that this is a 0, and it's going to provide a guarantee of message authenticity, even though the adversary knows exactly that's message 5. But the adversary can't do anything about the fact that it's message 5, can't fake it, can't modify it, can't decrypt it. So it's a good thing to be concerned about. And one thing you might have sort of picked up on in the paper is written in a slightly disconcertingly informal style. Like oh yeah, we got this protocol, let's try this thing, let's try that thing. You know, does this work, does that work? I don't know, it doesn't seem to break in this case, great. So I think you sort of see a difference between like 25 years ago, we had a much more heuristic and sort of ad hoc understanding how to reason about the security of these protocols. It was pretty good, but I think now you would see a much more rigorous statement that's not about, oh, well, we got to check, does it resist these 5 attacks? It's much more rigorous. Well, here's the plan. You just provide this property, that's it. You don't have to enumerate attacks anymore. So I think, crypto, especially practical crypto, has come quite a long ways in the sort of 2 decades since this paper came about. But yeah, there's a couple of advances. Like, for example, doing a MAC after encryption, it's like one thing that we now understand. You don't have to worry about MACs. You just do that, you're done. Yeah. Other questions? All right. So, okay, so this is how roughly you deal with these replay attacks over the network. Another kind of interesting attack I want to describe to you guys and show how we might deal with it has to do with a server being compromised at some later point in time. So this turns out to be a somewhat interesting problem. So here's the situation I want to describe to you guys. So the situation is we have some server like MIT.edu. It has a secret key. Here's a protocol. The server has a secret key, SKS. Only the server should know that key. But maybe somehow next year someone breaks into MIT's server. Or much like we were discussing a question earlier, like what if someone, in 5 years' time can guess this key because there's some advance in cryptography? That would be kind of unfortunate. So here's a puzzle. Like suppose that the adversary can get this secret key of the server. How bad is this? How damaging is it to our security? So what kind of suppose that you as an adversary got the secret key of the server. What can you do? Yeah? Okay, yeah, so your point is we can compromise future connections. So as soon as I compromise MIT to DDU, I can impersonate MIT to DDU. I can mount this attack we were describing, I guess, for which we were trying to use certificates. Right? So once I have MIT's secret key, I can start intercepting all the connections to MIT. I'll learn all the data being sent, all this good stuff. Is that as bad as it gets, or can we do something more damaging? Yeah? So that's an interesting question. If I happen to have records of how people talk to MIT's web server in the past, I can decrypt them retroactively. So that's kind of a weird property, which is that I break into MIT's web server today, and suppose I was expecting to break into it, like that was my plan all along, but I've been at it for years and years. But I knew I'd eventually break in, so I've been recording all the encrypted packets going to MIT's server for a very long time. I couldn't decrypt them then. But once I succeed in breaking to MIT's server and I get the secret key, now all those old packets that I recorded all of a sudden become useful to me. Because now that I have access to MIT's secret key, I can take this old trace, I can use the secret key to decrypt the session key from the third packet. And then I can use that to decrypt all the messages that are being sent. This is an extremely damaging attack in some ways, which is that I had some secret conversation with MIT's server, I sent some data to it, it sent me data back, and now all of a sudden, compromise 5 years down the line means my data is now public. So that's really disconcerting in some situations, or would be good to maybe avoid this problem. Does the attack make sense, the problem? So this is often called, I guess, the goal of avoiding this kind of problem is often called forward secrecy. So forward secrecy is a property that if our system had, we wouldn't have this problem. If a system has forward secrecy, then breaking a key later doesn't decrypt old conversations. So that would be a nice thing to have. And it turns out we can actually get this property with a fairly small change to our protocol. So let's try to sketch out what that would look like. And the basic idea for how we're going to get forward secrecy in our secure channel protocol is that we're going to only sign with long-term secret keys. So the reason, okay, hopefully this makes sense. So as a statement of like what we're going to do, if our server has a secret key like SKS for which it has a corresponding public key and a certificate, what we're going to try to make sure is that we don't decrypt stuff with that. We don't use that public-private key pair for decryption, because if we use it for decryption, then an adversary can come along and decrypt this thing later in the future. What we're going to do is we're only going to use these long-term keys for signing messages, and that's going to make sure that an adversary doesn't have anything that they can deduce retroactively. So here's what this protocol looks like. Let me just sort of sketch it out, and then we'll talk about why this works out well. So again, client connects to the server. The server has the public key of the server and a secret key of the server, but when a client connects, the server is going to generate an ephemeral key just for that client. It's also going to be a public-private key. It's going to be, let's say, pkcon and skcon. And this thing is going to be very short-lived. The server is going to delete that as soon as the connection is done. But while the connection is running, the server is going to keep this around. And what the server is going to do is going to send back a message to the client saying, the public key you should use is pkcon, not pks. And by the way, here's our certificate. Just to remind you, the certificate is a signature from SKCA that basically says, MIT is PKS. And it's going to send another signature by PKS, by SKS of pkcon. So what's going on here? Let me actually maybe finish the protocol first so that we know what we're talking about. Once the client gets this public key, it's going to encrypt the session key, K, with the public key of this connection. And then we can go ahead and encrypt the data as before. So why is this construction good? Well, one, let me try to convince you it's secure, and then we'll argue that it actually is even better. It's got this forward secrecy cool property. So the reason it's secure is that the client is going to encrypt the session key with this public key of the connection instead of the public key of the server. So that's one difference from what we were doing before. But that should be just as good, because the only person that has the corresponding secret key of skcon is the server. How do we know? Well, the server just told us. The server signed this message saying, only the server just freshly generated this pkcon, and it signed it for us with SKS. And we know that PKS is the corresponding key of MIT's server. So that's sort of the chain of argument. The client knows PKCA. It uses PKCA to check this signature to say that the certificate authority tells us MIT is this key. And then it uses this key to check that that server just told us, use this public key for the connection. So the fact that we send this key over to the server should be good. Make sense? All right. So why does this actually provide a stronger property of this forward secrecy? Well, the reason is that if an adversary gets access to SK of S, it can't really make any sense of these retroactive sessions because nothing is encrypted. Nothing is decryptable with SK sub S. If the adversary compromised the secret key skcon, then the adversary would be able to go back and decrypt old sessions. But if the server deletes these promptly right after the connection closes, that's fine. These things are nowhere to be found, even if the adversary breaks into MIT's server. Does this make sense? Questions about this forward secrecy construction? Yeah. No, yeah, well, I guess PKS is sort of implicitly sent as part of the certificate, perhaps, yeah. But what's used for actually encrypting some interesting data is PKCon. We can totally send PKS as well. No reason not to, yeah. Yeah?
The client really expects one key, one public key from the server, but here's being sent through. So is there presumably like some other part of the protocol that says, like, toggle this option where I'm sending you
Okay, so yeah, so you're asking, okay, well, we had this one protocol before, now it's a different protocol. How does the client know what to do? So far, we're playing this game where there's like one protocol. We always, in this new universe of like protocol version 5 that we're talking about, everyone speaks this version, and we expect this public key, this signed certificate, this PKS, this signed certificate. That's always the rule. We'll always use this one for this encrypted message. Now, okay, that's sort of just for exposition on the board. It's easier for me to do this. In practice, as you saw in the paper, if you evolve a protocol, now you've got to support both versions. Like the reason that there was this fallback from SSL3 to SSL2 is that at the time SSL3 came out, everyone was using SSL2. If they just had SSL3 not compatible with SSL2, like I'm sort of proposing on a board here, it would be bizarre. Like, you install this new Netscape browser, and the world stops working. No one would install it. They'd like get complaints. Everyone would roll back. So in practice, it's super important to support some degree of versioning and agreeing on exactly what the protocol is. And that turns out to be actually quite hard to get right, as you saw in the paper. SSL2 got this wrong, SSL3 got this wrong, even some version of TLS got this wrong. We think the latest version of TLS is pretty good about this now. But absolutely, this is like super tricky stuff because the initial parts of the connection are where we have to even agree. Like, you're going to be sending me 32 bytes or, 128 bytes. What do they mean? We haven't even agreed on any keys yet, but we still have to agree on these formats of messages. So there's no encryption or authentication going on yet. So it's very easy for an adversary to jump in these early stages and corrupt our packets and to mount attacks and to provide security in the face of these attacks during the initial handshake process ends up being a tricky thing to do because sort of nothing is authenticated yet. We can't really trust anything, which is kind of a weird setup. Make sense? Other questions about how do we do forward secrecy? So this used to be, I guess, how forward secrecy was implemented in some versions. Nowadays, there's a slightly fancier version of forward secrecy, mostly just because the underlying cryptographic scheme is different. but the latest version of TLS 1.3 gets forward secrecy by default, or achieves forward secrecy by default as well. Make sense? Questions? All right. So let's talk about, I guess, various things that, so far we've talked about this slightly strawman-like protocol that I drew up. Turns out to be fairly close to what SSL is. So I guess the real thing is SSL, which later turned into TLS. There's a bunch of complications in the real SSL or TLS protocol that we haven't really talked about so far. One of them, I guess we touched on briefly, which is versions and compatibility. So it's important in practice to talk to multiple versions of server implementations and that might speak different protocols. So the reason it's important to get right is that it'll later enable you to upgrade to a better protocol. So if you find a problem, it's good that you have a compatibility plan in mind, because it'll make it much more easy for you to deploy new versions of the protocol. The other thing that is quite a big pain in SSL and TLS is cipher negotiations. So far in all the diagrams I've been drawing, I've been sort of just, using sign without really much concern for like which signature scheme is it, or I just use encryption and I assume it's, I don't know, kind of AES. In practice, there's a whole bunch of different encryption schemes you could use, and at least the TLS protocol historically has wanted to support clients and servers agreeing on which cryptographic scheme they want to use between themselves. So it might be that a client and a server want to use AES to talk to each other, or maybe they want to use some other scheme, some other block cipher, some stream cipher. Who knows? It might be that they want to use RSA for public key operations, or they might use elliptic curve operations, and who knows what. So quite a bit of the complexity in the SSL and TLS protocols comes from the fact that not only do we need to agree on which version we're going to speak, first of all, but we also need to agree on which encryption scheme are we going to end up using once we agree on a key, and which encryption scheme are we going to use to agree on a key. So it ends up being a source of complexity and bugs. Another complication in the real TLS is that a server might actually have many certificates. And this might be the case if a server is hosting many different websites. In this case, it might be that a single server might be operated by some CDN, content delivery network, and it's got certificates for 1,000 different sites that are using that CDN. And now the TLS protocol has to first tell the server what certificate I'm expecting. Like I connect to a server, I can tell it, I'm expecting to talk to MIT or to Amazon.com. Might be the same server can actually speak for both. So the client first tells the server, I'd like to speak to this host, and the server gets to present back a cert saying, actually, I have a cert for that too. No problem. So there's quite a number of complications that arise in these real protocols that need to be solved somehow, but turn out to be slightly tricky. Right? Make sense? Questions? So one thing I wanted to show quickly is what the real SSL handshake looks like. So this is from SSL 3, so that sort of matches what you guys read about in the paper. TLS 1.3, slightly different, but not in any sort of deeply important way that we want to talk about now. So we basically see the same thing going on. So in the first step, the client sends some connect message to the server, and here, we send a version like we were talking about. There's going to be some randomness that the client sends that'll help derive random keys later, and some kind of a session ID for the session resume optimization that SSL supports, and a list of ciphers that the client is willing to support. Like I want to do DES with 40 bits, or DES with 64 bits, or AES with 128 bits, etc. Then once the client sends this first message, like in our protocol, the server responds with this second message, which I guess typically gets written out as 3 messages, but it's really one packet that gets sent back. So there's a version number from the server, some randomness, the ciphers the server wants to talk to you with. Then the server sends back its certificate or a list of certificates, because there might be multiple. And then it says, well, okay, that's all I had for you in terms of the certificate list. And at this point, the client is going to pick this random session key in the real SSL or TLS protocol. This is called a pre-master secret. This is basically the key K that we've been drawing on the board. And we'll talk a little bit about how this pre-master secret gets used in a bit. And then the client is going to take this pre-master secret and just encrypt it and send it to the server, encrypt it with the public key of the server. This is actually the version of SSL 3 that didn't even have forward secrecy yet. So it looks like our sort of more naive protocol version. And then here's an interesting property of the SSL specification that we haven't talked about so far. It's actually a pretty neat way to deal with a specific problem. The problem that SSL is trying to address with message 7 is exactly this issue of having just negotiated which cipher we're going to use, but this negotiation took place without any authentication or encryption. What I mean is that in message 1, the client told the server which ciphers it wants to use. In message 2, the server told the client, here's the ciphers I'm willing to use. None of that was authenticated. So if an adversary modified those messages, it could trick the client and the server to agree on a really weak cryptographic cipher scheme. So this is an attack that the paper describes from SSL 2. So here's the cool trick that's worth, I guess, understanding, is that SSL, once the client and the server basically agree on a key, which is related to this pre-master secret, what they're going to do is the client is going to compute a MAC with this secret key over all of the messages that were sent from the beginning of the protocol up to now. So you compute a transcript. Here's all the stuff you've told. So from the client's perspective, what the client is telling the server is, look, here's all the messages I think we exchanged. Message 1, message 2, message 3, message 4, message 5. I'm going to MAC all of them together, and I'm going to send you this MAC. And now the server, on its end, can check that the messages that the client thinks it used to agree on a key are the same messages the server saw to agree on the same key. If there's any discrepancy, like the client thought it sent one set of ciphers and the server got a different set of ciphers because of some attacker, this MAC is going to mismatch, and the client and the server can detect that something went wrong in this pre-authenticated part of the exchange. That's kind of a cool trick. Like this idea of authenticating a transcript of a protocol is a pretty powerful trick to do. Make sense? Questions about this trick? Yeah. No, here's the cool thing, right? Like this actually prevents downgrade attacks. And the reason it prevents downgrade attacks is that suppose an adversary modifies the client's message. It modifies this list of ciphers in message 1. The protocol is going to proceed. The client and the server are going to agree on something based on this modified message. But now the client is going to tell the server, hey, here's the messages I think I sent you. And the server is going to compute the same thing, but it saw a different message. And now the tag is going to mismatch. There's a little bit of an assumption here, which is that the adversary can't immediately break that MAC function right then and there. And this is the thing that they talk about in the paper. Like they think in this 40-bit of security, you can't mount a real-time attack on that. But modulo that, like unless you can really attack this thing and within a couple of seconds compute the fake MAC without knowing the key, then this transcript authentication plan actually works out pretty well. Question? So there's probably some kind of a time limit. The spec, I don't think, says explicitly, but probably you're going to time out after a couple of minutes. Like this is really intended as a secure channel protocol, so it's not intended for some thing that takes hours to establish. So probably the timeout is going to be on the order of minutes. Yeah. Oh yeah, export control laws, man. Yeah, that was an exciting adventure. So it used to be the case that the US said, you could use certain encryption schemes within the US, but you can only send 40-bit versions to outside of the US. And that basically made everything really insecure because everyone had to support these 40-bit versions for compatibility, and then you could downgrade to them. So that was a bit of a disaster. Yeah, we'll see. Right now, there's no sort of similar export control laws or anything like this, but, there's always sort of attempts. Every year you read someone's trying to pass a law to prohibit encryption or to make sure you have to give a copy of your key to someone. So that's not necessarily a given that this will continue, but for now, things are good. Other question? Yeah. So you're talking about, there was an issue that the paper talks about this change cipher spec not being authenticated. Oh, yeah. So, okay, so you're talking about attacks at a sort of a level above this protocol. So the attack you're talking about is that a web browser might try to connect to a server with HTTPS, and maybe HTTPS for some reason doesn't work out. So some browsers, it used to be the case that if they couldn't speak HTTPS over this encrypted protocol, they'd say, oh, well, maybe the server just doesn't speak HTTPS. Let me just speak regular HTTP. So that was sort of a downgrade attack at the next level up. The application would just downgrade to not even use TLS or SSL. Most browsers, actually every browser I know of, doesn't do that anymore, but this used to be a problem in some cases, yeah. Other questions? All right. So I guess there are some issues here the paper points out, which is kind of interesting. So one issue that the authors of this paper discovered is that the specification didn't actually MAC this message number 6 for some unfortunate reasons. And as a result, an adversary could actually drop this message and everything would still go through. This is kind of a weird message, I think for some compatibility reasons. But this message basically instructed the other end to start using the key that we just negotiated. And if you drop this message, the other end would just keep not using the key and could keep continuing talking in plain text mode, which is kind of unfortunate. So the way this was fixed in TLS 1.0, which is like the next version of after SSL 3, was that the spec said that if you get a finished message, you must have seen a change cipher spec message beforehand. Just like assume that was there, or like drop the connection if you didn't see that message before. So there's some little issues in SSL 3 that the paper points out that were there, but by and large, it actually works out reasonably well. So I guess there's like two more details that happen in the real protocol. So one is there's a sort of derivation of the master secret that gets used from this pre-master secret and the two randomnesses that the client and the server both supplied. So it's sort of an attempt to make sure that your session key actually is good if either the client or the server had good randomness. Sort of combines randomness from both to get a good key. In our naive protocol, we were just sort of basically sending the master secret right away from the client. And then the real protocol basically does this derivation of the K1 and K2 that we talked about there for encryption versus authentication. It sort of derives both of them by applying basically kind of a fancy hash function to this master secret. So instead of using the master secret directly, they derive K1 and K2 for encryption and macking by sort of hashing it together with these seeds again. Sort of make sense? Questions? So I guess the real protocol is a little bit more complicated than what we've talked about, but many of the parts are still the same, and sort of maybe the one idea to carry away from the real protocol is this cool trick of authenticating the transcript as a way to ensure handshake security. Question? So the counters actually get used in sort of this message 10 when we start encrypting and sending the data over. So I guess I didn't write them out in this text version of simplified protocol, but yeah, the counters get put into message 10 onwards. Yeah. Sense? Questions about this stuff? All right. So one thing that's useful to try to understand is what security properties do we actually get from the secure channel abstraction? So let's try to understand, let's say, data confidentiality. So to what extent is the data that we send secret? Can the adversary learn anything about the data? Yeah? Yeah, so actually not even really about block ciphers. Like any encryption scheme is going to leak the length. So one way to sort of think about this is, the secure channel, if you send 10 bytes versus if you send 10 gigabytes, it's going to send a different amount of data. one way or another. If you send 10 gigabytes encrypted, that's going to be a big ciphertext. If you encrypt 10 bytes, it's not going to be nearly as big. And in fact, usually the granularity is something on the order of either 1 byte or maybe 16 bytes or something fairly small. So the adversary can get a pretty good idea of how big the message is that you're sending. And actually, it's a little bit worse than this even, right? It's not just the length of the whole thing that you send leaks, it's that every write leaks. What I mean by this is that you might not send the thing as one giant 1 gigabyte blob. You might send, a header, and then you send another thing, and then you send something else. And the TLS implementation is going to take each thing you write to the secure channel, it's going to encrypt it and send it over the network. So each unit that you write to the secure channel is going to go over the network, and its length is going to be exposed. So the adversary can actually learn the sizes of all the different units of data that you're going to send over the secure channel. So that's a sort of a thing to worry about potentially. The paper mentions that this might mean that if you index the web and you know the sizes of all the web pages, you can probably tell, like, oh, if you got a web page of this exact number of bytes, that's that web page, and so on. So this could be kind of damaging, yeah. Yeah, so many schemes implement various degrees of padding. The more you pad, the more coarse-grained this data becomes, and the more inefficient it becomes. So at some level, like, you can probably tell if it's 10 gigabytes or 10 bytes. You're not going to pad to 10 gigabytes. That's going to be crazy. But you can pad to within some amount. The thing to keep in mind is that padding, padding doesn't work so well if the adversary can somehow add extra bytes to the data. So maybe if the adversary can set an extra HTTP header or like a longer cookie, maybe that length of the cookie will just push you over the boundary of the padding. So if the adversary is particularly sneaky, they can maybe use other parts of the system to somehow cancel out the padding or get you just on the verge of either padding one extra block or not to learn exactly what you're doing. So, padding hides something, but it's actually surprisingly easy to bypass in various ways. Another thing that does leak in TLS is the timing of when the data is being sent. So if the server sends, the header now and the body 10 milliseconds later or 100 milliseconds later, that is totally visible to the adversary as well. So like the secure channel thing, we had this nice diagram of the pipe, but this pipe is kind of a complicated pipe to really understand what properties it gives us. In terms of integrity, of protecting the sort of authenticity of the data, things are pretty good. The one exception of what TLS doesn't guarantee about integrity is the sort of EOF flag, or like end of file, or when is the data done. And this is because TLS servers, like HTTPS servers, they'll just like close the TCP connection when they're done talking to you. So when the connection is closed, that's all the data you're going to get. But there's no authentication of that being the end of the data. So it could be that an adversary shoots down your TCP connection with some attack like what we were talking about on Tuesday by guessing a sequence number. And at that point, the adversary can cause your TCP connection to stop. The client might just think, well, yep, I got some data. That's it. The TCP connection, that's all the data I'm going to get. That's what the server sent me. But in fact, it might have just been a prefix of what the server wanted to send you. So it's a little bit hard to really convince yourself that you got what the server was trying to send you, but you definitely got some prefix of it. So TLS does give you that guarantee. And in terms of privacy, privacy is sort of a weird, catch-all in some sense. But one thing that TLS definitely does not hide is IP addresses. So the adversary can certainly tell which client and server are talking to each other. The adversary can also even tell the server name, because typically the client actually tells the server, here's the URL or the server name I want to talk to in order to fetch the right certificate from the server. So the adversary has access to a little bit more information from TLS as well. So this is sort of all to say that TLS is a pretty clean abstraction of a secure channel, but even that has a number of caveats that are important, especially some of these data confidentiality leakages. These guys get actually used in practice to infer by some adversaries what websites you're browsing, for example. Does this make sense? Questions? Yeah.
Is there any worry when a client sends a request to a server in that top board? I mean, this server is sending back a lot of data. Can an attacker spoof their
Yeah, so I think you're absolutely right in thinking this could be a DOS sort of amplification vector. One nice thing is that this runs over TCP, so you'd have to basically spoof a TCP connection. But yeah, if you can spoof a TCP connection, this will send a big blob to the client, for sure. There are some protocols that actually use TLS over UDP, those are wonderful amplification sources from a structure's perspective, yeah. So you need to do worry about these kinds of issues. Maybe a bigger issue in some TLS contexts is by sending a fairly simple request to a server, you're going to cause the server to do some expensive crypto on its server side. That could be another DOS attack where I'm just sending a small packet and the server chews up 100 milliseconds of CPU time. That'll also be a big DOS vector for potential adversaries. Yeah. So things to worry about. Yeah. So there's. I don't know if anyone has a particularly great solution. Just sort of over-provision as usual for many DOS attacks. All right. Any other questions? Okay, so that's it for TLS. This is our first sort of example of using crypto to build something in network security. We'll have a bunch more lectures coming up in looking at other ways crypto gets used, including some guest lectures we'll have later on about, for example, how Zoom does crypto as well. But that's it for this week. See you guys on Tuesday. We'll talk about certificates.